All right, nuclear chemistry. This is actually my favorite section out of the whole course. So um, I'm in for a treat. I don't know about you guys. So, in order to understand nuclear chemistry, I'm going to back up way to the beginning of the course when we discussed what an isotope is. Please just remember that an isotope is an atom of the same element, but it has a different number of neutrons, which means that it has a different mass. So again, when we're looking at an isotope, I can write it out in a couple of different ways. One way I could write it is to write, over here on the right, Cl with a 35 and then a 17. This number down here, this is Z, German for number, right? Z for Zahl. That's the number of protons. So that defines what element you have. If you didn't have 17 protons, you wouldn't have chlorine, right? If you suddenly had something like 18 protons, you'd actually have argon. It would be a completely different element. Now, this number up here is A, and this is the mass number. It's the number of protons plus neutrons. So if I asked you to tell me how many protons, you'd say, well, it has 17 protons because of this number here. It would have, let's see, to figure out the number of neutrons, it would be 35 minus 17 would be 18. So I would have 18 neutrons, okay, due to this mass number here. Now I could also write this in a slightly different way. If I'm lazy, I could just write Cl35. This one's easy because you can just type it straight into Microsoft Word or whatever without trying to do something kind of funky like this thing here. What does this mean though? Cl35 tells me it's chlorine, and it tells me the mass number, but it doesn't tell me the atomic number, right? So to get the atomic number, I'd have to pull out my periodic table, and then I'd see, oh yeah, chlorine, that is atomic number 17, and so I could just look it up. So, each method of writing it has its pros and cons, but that's kind of the overall picture of it. Now, let's get into something new. Well, it turns out that some of the isotopes are actually radioactive, or they're known as radioisotopes. They're unstable, and they will break down to either emit particles or energy or both, and they do so in an attempt to kind of reach a nice stable conformation. All right, so and we'll talk about the different types of particles and energy that they give off, but that's known as radiation. And radioactivity is being actively, giving off radiation, and so it's the process of actually emitting that radiation. So let me give you an example. There are actually 3 isotopes of hydrogen, and sometimes called, just regular hydrogen, and then deuterium and tritium, so you might have heard that before. But what does this mean? Well, it turns out that one of these is radioactive, and there's no way just to look at it and know, but it turns out that tritium, this one right here, is radioactive. And so you can actually, see if you look at exit signs, like the old green ones. If you look at the bottom of it, it'll probably have a little radioactive symbol on there to indicate that it does have tritium in there and is radioactive. So don't break it open with a baseball bat and eat it if you get snacky. All right, I probably just saved your life right there. So anyway, but you can see that each of these has exactly 1 proton, right? That's what makes it hydrogen. This one actually has 0 neutrons, because 1 minus 1 would be 0. This one would have 2 minus 1, so this would have 1 neutron, and then tritium would actually have 3 minus 1 would be 2 neutrons. So you can see that they have different numbers of neutrons. So what are the different types of radiation that can be given off by a radioisotope? Well, the first type is alpha, all right, given the Greek letter alpha, and this is actually a helium nucleus. So sometimes you'll just see it written, as an alpha, but I much prefer that you write it like this, 4,2 helium. You'll see why when we actually balance radioactive equations so that you can see kind of what's going on. But as a helium nucleus, it has 2 protons, 2 neutrons, and because it doesn't have any electrons, it actually has a +2 charge on it. So this is a pretty massive form of radiation. I mean, this is, has about a mass of about 4 atomic mass units. So compared to everything else, this is huge, right? So this is a lot like taking a bowling ball out into your flower garden, right? If you try to roll that or throw that that bowling ball, it's not going to go very far because it's just so massive that it can't really roll very far in your garden. But it's going to pretty much demolish any flowers that it comes in contact with. This is a lot like an alpha particle, big old massive particle with a huge mass. It's the highest mass of all the different types of radiation, but it has the lowest penetrating power. It can't get very far because it's so large. In fact, a few sheets of paper or a couple of inches of air will actually block alpha particles. So when you're being exposed to alpha radiation, it typically just hits the dead skin cells on the outer layer of your epidermis, and you don't really have to worry about it unless you were to actually ingest those alpha particles, and then those radioactive bullets are shooting out in your stomach, and that can cause problems. The next type of radiation would be beta particles. All right, so given the Greek letter beta, or you can write it 0 minus 1e, which is the better way to write these things. So this is a high energy electron that's actually being shot out of the nucleus. So it's not just a normal electron kind of floating around that can be transferred from one atom to another. This thing is like super high energy that comes blazing out of the nucleus itself. As an electron, it has a -1 charge, and it actually comes from a neutron. So if you have a neutron, it can actually decay, turning into a proton and a beta particle. Right? Beta particles are negative, protons are positive, so it makes sense that when they combine, you actually form a neutron. So this form of radiation has a negligible mass, right? Electrons are very, very low mass, and it has a moderate penetrating power. So in this case, it can penetrate a little further. When I was in graduate school, we used to use radioactive phosphorus to tag DNA, and when we were working with it, I would always make sure to have gloves and a lab coat on, and then I would use a little plexiglass screen, maybe a centimeter of plexiglass, that would help to block any beta particles that were given off. All right, so this is kind of like taking a baseball out into your flower bed. You can roll it. It's going to get a little further than a bowling ball, right, just because you can throw it further, but it's not going to do as much damage to each of those flowers that it comes across. The next type of radiation is actually just kind of a subset of the previous type, which was beta particles. So positrons are sometimes just written beta plus, or they could be written 0 plus 1e. And these are actually antimatter, right? This is the antiparticle of the electron, which means equal mass but opposite charge. So an electron has a -1 charge, a positron has a +1 charge. These actually come from protons turning into neutrons. So a proton will radioactively decay, turn into a neutron, and emit a positron in the process. Now, if you are a Star Trek The Next Generation fan, which I totally know you all are, since you're all Trekkies, it turns out that Lieutenant Commander Data, right, is an android, and he has a positronic net for a brain, right, instead of an electronic net. It runs on positrons. Interesting, right? So these are actual real particles, but because they have the same mass as an electron, as a beta particle, they will have the same mass and the same penetrating power. So just the exact same level as the beta particles previous. Now the next one would be gamma rays. And if you remember the old Hulk show with Lou Ferrigno, gamma rays is what turns the Hulk into the Hulk. So another form of radiation. These are actually just high energy photons. So it's just a form of light energy, right? Which means no mass, no charge. It's just energy, but it's a decent amount of energy, right? High energy photon. And because of this, it has the highest penetrating power of all the forms of radiation. So for alpha particles, you just need a few sheets of paper to stop an alpha particle. Beta particles or positrons, you typically just need a centimeter of plexiglass. To stop gamma rays, you're going to need a couple of meters of concrete and or lead, right? So these are much higher penetrating power. I like to collect a lot of random radioactive stuff, and I'll show you some on the next slide, but I don't have any gamma ray emitters because, again, there's no really safe way for me to store these. Whereas everything else, I keep it in a plastic kind of briefcase thing, and the plastic stops all of the alpha and beta particles that are being given off. All right, so just for fun, I'm going to go ahead and show you a few of my radioactive things from my collection. So the first one, actually down here in the bottom right-hand corner, this is known as Trinitite. So when the U.S. was actually testing the first atomic bomb, it was nicknamed Trinity, right? The Trinity tests, and they took it out into the deserts of Alamogordo, New Mexico in 1945, and they actually dropped these bombs on the desert, right? And the heat from the blast was so hot that it actually melted the desert sand into glass. And so these are actually chunks of that glass, and even today they're still radioactive. And it's actually a federal offense to go and collect more of this stuff. If you already have it, it's perfectly fine, but you just can't go and dig up more of it if you want to. So the next one would be right here. So in the top right-hand corner, this is a piece of Fiestaware. This is a little plate, and in the 50s and 60s, Fiestaware, used different heavy metals in their glazes to give them different colors. And I have a yellow plate that has lead in the glaze. Not a big deal. It might give you a little bit of lead poisoning if you eat off of it. But this mango orange color actually comes from uranium that they used to put in the glaze. So they would literally put uranium into this, and this plate is extremely radioactive. Kind of crazy, especially because you can see where the glaze is kind of flaking off there in the center, and so you're actually ingesting little bits of uranium, and then it's radioactively decaying in your stomach and causing all kinds of damage. Or anytime you eat something that's acidic, like marinara sauce, it could actually, start to dissolve the uranium into the food. A couple of years ago, we were at a party, and the woman pulled out some Fiestaware, and she said, "Oh yeah, this is my grandmother's Fiestaware." And I said, "Oh, that's great." And I turned to my kids and whispered, "Don't eat off the orange ones." Very dangerous stuff. All right, so another example, it would be here in the bottom left-hand corner. So this is a clock, but it happens to glow in the dark, and even today it glows in the dark. This is from about the 60s, and the paint actually contains radium. So the paint all over the hands and the numbers contains radium. It's a really sad story. You should Google radium girls and find out more about it. But what happened was that they used to have young women work in these factories where they would sit there and paint this radium paint onto the watch dials and clock faces and so forth. And in order to get a sharp point on the paintbrush, they would actually smooth it with their lips, or kind of just lick the end of the paintbrush to smooth it into a sharp tip in order to get the really fine detailing. And so they were ingesting bits of this radium, and because they didn't know it was dangerous, they would sometimes paint their teeth with this paint, or their fingernails, or put streaks in their hair and so forth, so when they'd go to parties they would glow in the dark. And it wasn't until years later that they started to have massive problems. They would die of cancer. They would sometimes their bones would literally just crumble. Right, they'd be walking across the room and their femur would just snap in half. So very sad, because radium is in the same group, the same family, the same column as calcium, and so your body interprets it when it ingests some radium. It interprets it that it's calcium, and so it actually shuttles it off to your bones, where it's incorporated into your bones, where it radioactively decays and literally just kind of shoots little holes in your bones, and they kind of become honeycombed and just disintegrate. Another example is, back in the 50s and 60s, people were stupid, and they didn't know about the dangers of radioactivity, and so they would actually they had this thing called a Radithor, which is kind of the Gatorade, the sports drink of the day, and they would drink this stuff. And there was a wealthy billionaire playboy guy named Eben Myers, and he actually used to drink about 2 bottles of this a day, and everything was fine until his jaw literally just fell off. The bones just crumbled, and they had to surgically remove it. So very, very creepy stuff. So they used to do a lot of interesting things. They actually had these things known as fluoroscopes, which would be at shoe shops, right? And when you go and you're a kid and you'd get a new pair of shoes, and your mom would sit there and push on the toes to see if it fits and how much room you have to grow. Well, imagine instead putting your foot into a fluoroscope, which is just an unshielded X-ray. and they would literally just, you could see your toes wiggling around in the outline of the shoe, and then the shoe salesman and your mom could sit there and look at it and decide whether the shoes fit you or not. So I don't have one of those, but it'd be kind of cool to have one. Also, let's see. Over here on the top left, I have a neutron irradiated dime from the American Museum of Atomic Energy. Now, with all of these things, when something's radioactive and you're exposed to it, it doesn't make you radioactive, right? It's not like Homer Simpson where he works at the power plant and suddenly he starts glowing at night. It doesn't work that way. If I, hold my hand over that Fiestaware plate, it can damage my hand, right? It gives off alpha particles which can hit the skin cells and can damage the skin cells, but it doesn't suddenly make my hand radioactive. All right, it's kind of like if I took a paintball gun and I started to shoot my hand with a paintball gun. I could damage my hand, but it doesn't turn my hand into a paintball gun. It wouldn't make any sense, right? So the only way to make something radioactive would be if you were to actually ingest or inhale something that's radioactive, because then the particles are actually inside of you, and then they're, exposing your cells to radiation. So even then your cells aren't radioactive, but those radioactive particles are inside of you, kind of blasting things apart. But you can actually do something called neutron irradiation, where you bombard an element with neutrons to force it to become radioactive. And so that's what would happen at the American Museum of Atomic Energy back in the 50s and early 60s. Back then, all of the dimes were silver, right? So you take a silver dime out of your pocket, you'd pop it into the machine, and it would neutron bombard it and actually force some of the silver atoms to become radioactive. It would then, drop it into a little, container that had a Geiger counter and go, and you'd hear it kind of like crackling because it would tell you that it's radioactive, and then it'd spit it out, and you'd say, "Look, Mom, I have a radioactive dime," and you could go to the gift shop and buy a little, coin case for it and stick it in your pocket next to your goods where you're damaging it all with radiation. Not a terribly good idea. The dime's no longer radioactive because the half-life of the silver was very low. I'll talk about half-life in a little bit. So no longer radioactive, but kind of an interesting piece. And so in all of these cases, you're probably thinking, wow, radiation is like a dangerous thing. It's scary, something I should worry about. Well, yes and no. All right. Radiation can damage cells, but it can also do a lot of good things, right? So one of these good things is that each of you hopefully has one or more smoke detectors in your home, because they save lives, right? And if you were to open this up, you'd actually see inside of there a little, you can kind of see the outline here. It's like a little black, mesh container thing with a little silver, metal disc on top. And scratched into that silver metal disc is the radiation sign, the radioactive symbol. And so the reason for that is if you were to break that open, you'd see a little tiny kind of asterisk-shaped disc. It's extremely small, and it's actually americium, radioactive americium-241, that's been gold-plated. And that's how smoke detectors work, is that the americium radioactively decays via alpha particle emission. It bombards the air molecules, which then ionizes them because it hits them with so much energy. So it gives them a charge, and then that allows a current to pass through the air in that little ion chamber there, and then the smoke detector doesn't go off. But if smoke gets in there, or water vapor because you left the shower door open again, and the smoke alarm starts beeping, those water molecules or smoke particles get in there and they block that, alpha particles from, creating that circuit or closing that loop, and so therefore the smoke detector starts to beep. So, americium seems like a really dangerous thing, and yet it saves countless lives due to smoke detectors. So this is just a sampling of some, fun radioactive things. It turns out that I have some radioactive toothpaste from World War II where they used to put thorium in it. Lantern mantles, those little cloth baggy things that you put into a gas lantern, those are highly radioactive. They even used to make things like radioactive condoms. I don't know who thought that was a good idea, but anyway, they had all kinds of crazy things. So anyway, moving on. let's go ahead and talk about what radiation does to us, right? That's what we usually care about. So it turns out that you cannot detect radiation just using your senses. You can't walk into a room and say, ah, my spider sense is tingling. No, it doesn't work that way. You need a Geiger counter, which will start to click whenever it's exposed to radiation, or you can use scintillation counters and different tools, but a Geiger counter works really well. All right. Now, radiation can actually damage or kill rapidly dividing cells. So, if you're exposed to radiation through, radiation therapy, it can damage your bone marrow, your skin, reproductive and intestinal systems because those cells are rapidly dividing. And so, think about what happens. Your immune system lowers because you're damaging the bone marrow. You can sometimes get sores. It can make you sterile because it's damaging your reproductive tract. You usually get kind of like radiation sickness, nausea, and so forth because it's damaging your intestinal systems. And the reason that we do this is because cancer cells are also dividing extremely rapidly. So the idea is by hitting a tumor with radiation, you're damaging those cancer cells enough that hopefully they can no longer survive and they die off. And hopefully you do this before you actually end up damaging the surrounding tissue too much. And it's kind of a double-edged sword because radiation can cause cancer by damaging cells, but it can also cure cancer by killing off the cancer cells. So just something to be aware of. One more thing you might want to check out, especially if you live in New England like I do, it would be to test your home for radon. So radon is a colorless, odorless gas that's constantly coming out of the ground, especially in the granite bedrock of New England. And so it's leaching out of the ground. And when we bought our home, we actually had it tested, and the levels were high enough that the expert said that if we had 1,000 people living here, probably about 8 of them would develop lung cancer due to the radiation from the radon gas. And it's again, you can't detect it using your normal senses. It's heavier than air, which is why it kind of gets trapped in the basement. And so the solution was to actually install a radon ventilation system, which kind of pumps out the radon gas and actually blows it up and out over the neighbor's house. No, but it's so weird, but they always say that dilution is the solution to pollution, right? This radon gas isn't a problem. I mean, it's naturally coming out of the ground, out of your lawn and stuff. It's only a problem when it gets concentrated or trapped within an area like your basement. And so you just need to kind of spread it out and get it out of your home. Now, one nice thing about radiation is you can actually use it to irradiate food. So you can take things like strawberries. I don't know about you, but when I buy a thing of strawberries from the grocery store, it seems like by the time I get it home, it's already moldy. I hate that. So by irradiating it, by exposing the strawberries to gamma rays, you can actually kill off all the mold spores and the bacteria and so forth because they're living, right? And you kill that off. The strawberry itself isn't alive, and so you don't need to worry about damaging that. And in the process, you kill off all this nasty stuff, and it makes the shelf life, much, much, much longer. All right, and it does not make the food radioactive, right? It's definitely not radioactive. Now, they also can do the same thing with ground beef to kill off like the E. coli and so forth. And again, it makes it much safer to eat, and it does not make the food radioactive in any way. So enough with all the fun stuff. Let's go ahead and dig in. Well, actually, this is still fun stuff, but so let's go ahead and dig into nuclear equations and reactions. So when something radioactively decays, it's going to give off radiation. And we can actually write this as an equation, kind of like a chemical equation. And just like a chemical equation, we need to balance this thing. But it's far different than balancing a normal chemical equation, because during normal chemical reactions, you cannot transmute elements, right? If you start with a carbon atom, you need to end up with a carbon atom. But that doesn't work so well with radioactive equations, because it turns out that you actually can change elements. So you might have an original nucleus here, let's say radioactive phosphorus, and then it can give off a form of radiation, maybe a beta particle, and it'll actually form sometimes can form a new nucleus. So instead of having radioactive phosphorus, now you have sulfur. and a beta particle coming off. And so this is kind of interesting that you can literally change one element into another. In fact, you can even change lead into gold, and they've done this in a nuclear reactor by bombarding, the lead and changing it and so forth and having it radioactively decay. It's just like 1,000 times more expensive to do that than to just dig gold out of the ground, but you can literally change one element into another. So if we can't just count atoms, how do we balance a nuclear equation? Well, we're going to make sure that the following two numbers match up on both sides of the reaction arrow or the equation arrow. The first is we need to look at the sum of the mass numbers, that top number, and make sure that those are the same on both sides of the arrow. And then we're looking at the sum of the atomic numbers, that bottom number, and making sure that that adds up to the same thing on both sides of the arrow. Let me go ahead and give you an example of this. So let's look at my happy Fiestaware, right? So this has uranium in it, which is radioactive, and uranium actually gives off an alpha particle. So sometimes, I might just say, uranium-238 gives off an alpha particle, and I might just write it like this, but what you should do is you should immediately write it as 4,2 helium, because we're going to need that to balance our reaction here. So let's go ahead and double check that everything adds up, that this is a balanced nuclear reaction. So let's look at the top number. The top number is 238 over here, so this adds up to 238. On the right hand side I have a 234 and a 4. That adds up to 238, so I know that that top number, the mass numbers, are balanced. What about the atomic number? That bottom number is 92 on the left hand side of the arrow. A 90 and a 2 adds up to 92, so therefore this is a balanced nuclear reaction. And what it's telling me is that uranium breaks down and it gives off an alpha particle, and then in the process it becomes thorium-234. Okay? So let's go ahead and look at an example of beta particle emission and make sure that this one balances out nicely. So carbon-14, which is radioactive carbon, decays via beta particle emission. So let's go ahead and double check that this is a truly balanced equation. Well, first thing we notice is that we do have a beta particle over here, right? 0 minus 1 electron, so that's good. Now, let's look at the mass numbers. I have 14 here. 14 plus 0 on the right adds up to 14. So that works. On the bottom I have 6. Over here I have 6 plus a negative 1. Sorry, 7 plus a negative 1. 7 plus a negative 1 comes out to be 6. So this is a nice balanced beta particle emission. And you'll notice that in each of these cases we truly are converting one element into another. Let's go ahead and look at a positron emission. So in this case we do have a positron. It's a 0 plus 1e. And notice that the mass number on the left is 11. On the right hand side it's 11 plus 0, adds up to 11. Down here we have 6. 5 plus a positive 1 is 6. Therefore this is a nice balanced positron emission nuclear reaction. And now let's look at gamma. Gamma is a little weird because notice that gamma, back up 1 second. Alright, notice that gamma is a 0, 0 gamma, right? Which means that it's not going to change the mass numbers at all, or the atomic number. So what's happening here is, notice that in the top left-hand corner it says 99M. That means metastable. So this is a metastable, or mostly unstable form of technetium. And so the top number is 99 there. 99 plus 0 is 99, and then 43 on the left. 43 plus 0 is 0. So notice that we went from technetium into technetium, right? So we didn't actually change the element, but it went from the metastable isotope to a nice stable version of it by giving off that extra energy, right? It's kind of like it's jittery and excited, and it needs to do something, and so it gives off that energy, and then now it's nice and calm. Kind of like when I take my kids to the park and it's like, here, just go run, burn off some energy, right? Come back when you're a little more calm and not so crazy. So let's go ahead and practice. Let's talk about americium-241, which is the element that's in your smoke detectors. And notice that I tell you in this case that it's giving off an alpha particle, right? And then some kind of mystery isotope here. So the first thing I'm going to do is I'm actually going to rewrite this. So this is 24195 americium. Okay, I have my mystery isotope, and then I have an alpha particle. Now instead of just writing alpha, which doesn't give me any information, I'm going to rewrite that as a 4,2 helium nucleus. Now the reason that that's helpful is because now I have some numbers to work with, right? So notice that the top number here, the mass number is 241. Here is a 4, so the mystery element must have a mass number of 237, because 237 plus 4 equals 241. Okay, what's my bottom number going to be? My atomic number? Well, here's 95, here's a 3. The only number that would work would be a 93, because 93 plus 2 is 95. So now I need to actually figure out what is that mystery element. Well, I pull out my periodic table and I'm going to look for element number 93. Okay, so what's element number 93 on the periodic table? Neptunium, named after the god of the sea, right? So Neptunium, and so what's happening here is my americium is radioactively decaying, giving off an alpha particle, and turning into Neptunium. So that is a balanced radioactive equation, or a radioactive reaction, right? Let's go ahead and take a look at our next nuclear reaction. Well, in this case, I give you P32, right, radioactive phosphorus, and tell you that it's decaying via beta particle emission. All right, so what's a beta particle? Well, beta particle is 0 minus 1e. So I'm going to go ahead and write it like that, because it'll be a little more useful than just having this beta sitting there. Okay, so our next thing is we need to go ahead and figure out what our numbers will be. Well, here we have a 32. On the right hand side we have a 0. So this number must be 32, right? Everyone agree with that? Good. All right, the bottom number here is 15. Here I have a negative 1. So something plus negative 1 equals 15. Well, it's got to be a 16, because 16 plus a negative 1 is 15. Now all I have to do is look at my periodic table, and I notice that element number 16, atomic number 16, is sulfur. And so therefore, the phosphorus is radioactively decaying and turning into sulfur via beta particle emission. All right, one more. This one's a little trickier, but not too bad. This is radioactive cobalt. So oftentimes in hospital settings, they'll use radioactive cobalt for radiation therapy, and it happens to give off beta particles and gamma rays. Ooh, double trouble. So let's go ahead and try one of these and see if we can figure out what's going on. Well, the first thing I'm going to do is, just like always, I'm going to go ahead and rewrite this. All right, so I have my mystery element, and then I have a beta particle, which is 0 minus 1e, plus a gamma ray. I'm going to go ahead and write it 0, 0, gamma, just so that we can clearly see that it has no mass, no protons, nothing, right? Okay, so what is my mystery isotope here? Well, first thing I need to do is to go ahead and look at the top number, right? So here I have a 60, 0 and 0. Well, this must be a 60. All right, here I have a 27, 27. Ooh, here I have a negative 1 and a 0. So the only thing that would work here would be to put a 28, because 28 plus a negative 1 plus a 0 sure enough comes out to 27. Pull out my trusty periodic table, and I look at element number 28, which is nickel. So it turns out that my radioactive cobalt is decaying and turning into nickel. So over time, the entire cobalt source is, giving off these particles and energy, and it's all turning into a big pile of nickel. So as something radioactively decays, it does so at a predictable rate, what's known as the half-life. So the half-life, or the T1/2, is the time it takes for 1/2 of your sample to radioactively decay. And it turns out there's absolutely no way to change the half-life of a radioisotope. So radioactive phosphorus has a half-life of about 14.1 days, so about 2 weeks. And there's nothing I can do. I can't change the temperature, the pressure, nothing will actually change how quickly that decays. And so let's go ahead and imagine that that is, here I have this container. Notice that, I just made it easy by showing that I have, 1, 2, 3, 4, 5, 6, 7. I have 8 little, atoms of, let's say, radioactive phosphorus. And after one half-life, now half of it has decayed. And so now some of it has turned green, right? Now it's decayed from phosphorus into sulfur. So now I only have 4 atoms of my radioactive stuff. Now notice that I still have, other atoms, but I don't have as many of my original radioisotope. After another half-life, I'm going to have half of that. So instead of 4, I'm going to have 2. After another half-life, I would have 1, and so forth. And so over time, it radioactively decays, and at some point it reaches such a low level that you don't even worry about it, because there's always some background radiation that we're exposed to just from radon in the air and cosmic rays and stuff. And so at some point, the radiation level is so minimal that we don't even really consider it to be, a hazard. Now, one question that people often have is there really a safe level of radiation? Well, technically no, right? Because, if, you just happen to get unlucky and you have this, let's say that a newborn baby takes its first breath in the hospital, and it happens to breathe in an atom of radon, which is radioactive. It decays, and that can, maybe that just happens to hit a cell, which just happens to damage the DNA in just the wrong spot, which just happens to, trigger the formation of a tumor, right? And so that poor unlucky baby just got cancer on its very first moment of, being in this, world. And that's possible, right? But it also could be possible that you could be breathing in radon gas your entire life, and it just never happens to damage, your cells enough that it actually causes cancer. It's kind of like if I take a paintball gun into, a crowded classroom, and I just start randomly, firing this paintball gun. Those paintballs, most of the time, will just hit, the ceiling and the desks and stuff. Every now and then it might hit a person, but most of the time it might hit them in the arm or the clothes or, something where it doesn't really do any damage. But every now and then some unlucky bloke gets hit in the eye by a paintball, and then they hurt, right? So it's the same type of thing. You could be exposed to radiation for years and years and years and years, and nothing happens. And yet, it also could be that you're exposed to a tiny little bit, and you get cancer. So, you can spend your whole life in fear of radiation and UV light from, the sun and so forth, or you could just take sensible precautions and go about your life. And that's what I do, is I try to avoid things that are high in, radiation or that are highly radioactive. But, I'm also not afraid and think, oh no, I just breathed in an atom of radon because I was taking a walk outside. Well, no, I'm always going to be breathing in radon, tiny amounts of it, but I avoid situations in which I might be breathing in large amounts of it. Now, one little thing as I stand on my soapbox for a second, if you are really afraid of radioactive material, the very worst thing you can do is smoke cigarettes, because cigarettes actually contain very high amounts of radioactive material. You can take a Geiger counter and check it, and it'll start clicking. And so it turns out that if you smoke a pack and a half of cigarettes a day, which is quite a bit, but if you smoke a pack and a half a day, you are exposing your bronchial epithelial cells to the same radiation level as if you got about 3.5 chest x-rays every day of your life. And that's a lot of radiation that you're being exposed to, and that's just the pure radioactive stuff, not talking about carcinogenic chemicals and all the other nasty stuff that's in there. So, a lot of people, when they go to the airport, like here at Logan Airport, they have you walk through that little body scanner, and people freak out, and they're like, oh, I don't want to be exposed to the radiation. Well, the level's so small that you're being exposed to like 100 times more just walking in the door and breathing in someone's, breath of secondhand smoke. So again, be careful with radiation, but don't live in fear of it. I should also mention before we move on that you can't really escape radiation because you yourself are radioactive. You have, some atoms of radioactive carbon inside of you. You have some radioactive potassium and a bunch of different elements of radioisotopes that are just naturally existing in your body. And so you yourself are slightly radioactive. So, all right, anyway, let's go ahead and talk about radioactive iodine. This is actually used a lot in medicine because iodine is taken straight to your thyroid gland. So if you happen to have hyperthyroidism or thyroid cancer or something, they'll actually give you this radioactive pill, radioactive iodine, and your body shuttles it straight up to your thyroid where it does its work, it damages the cells and kills them off, and then hopefully cures the problem. And the only problem is now you're excreting radioactive iodine in your sweat and your urine and so forth, and so they have to actually collect all that and take care of it. But anyway, so the half-life of iodine-131 is about 8 days. So if I start with 100 milligrams of it, how much will I have after 32 days? Well, if I start with 100 milligrams, after 8 days, how much will I have? Well, it's the half-life, so I'll have half of that. Now I have 50 milligrams. All right. After another 8 days, how much will I have? Well, 25 milligrams, because I have half of that. Okay. What about another 8 days? Well, now I have half of that, so about 12.5 milligrams. And I'm going to curve it around down to the bottom here. So after another 8 days, how much do I have? Well, half of that, so about 6.25 milligrams. And notice, let's see, how long has this been going on? I have 8 days, 16 days, 24 days, 32 days. So after 32 days, I now have about 6.25 milligrams, about 6% of what I started with. So that's what half-life is. Let's try another one. Let's say that you have some radioactive phosphorus, P32, has a half-life of about 2 weeks. So in this case, I'm starting with 20, back up. Get my little pen out here. Okay, so in this case, I'm starting with 24 grams. I have a lot of this radioactive phosphorus for some reason. All right, after, the half-life is 14 days, I'm just going to go ahead and call that 2 weeks. Fair enough? So after 2 weeks, I have 12 grams, right? I have half of it. After another 2 weeks, I have 6 grams. And after another 2 weeks, I have 3 grams. Okay, so this has been 2, 4, 6 weeks. So after 6 weeks, I only have 3 grams. All right, so that's what half-life is. There is a formula for when you're doing more complex problems, but at this level, this is all you really need. So how do we actually measure radioactivity? Since you cannot, detect it with your senses, well, we use, specialized tools like Geiger counters in order to do this. And the units are a little bit weird, but we're going to be measuring things in disintegrations per second, right? So we're counting how many atoms, decay every second, which seems kind of crazy, but it's how we do it. There are some units. I'm not going to, worry too much about these, but there are becquerels, which is named after Henri Becquerel, who discovered radioactivity, and this is 1 disintegration per second. A Curie, named after Marie Curie, is 3.7 times 10 to the 10th disintegrations per second. And so you can use millicuries. When I was in the lab, we worked a lot with microcuries. So we might add 10 microcuries of radioactive phosphorus to a reaction or something along those lines. Now that's great to measure things in, disintegrations per second. However, that doesn't really tell us how it's going to affect us. So oftentimes people will use something like RADS, radiation absorbed dose, and this is the amount of radiation absorbed by 1 gram of a substance. Okay, so that's a little better. It tells us what's happening, or the amount of radiation that's actually absorbed by somebody by 1 gram of a substance. But what if it's bone versus hair or skin or stomach lining? Okay, it's going to change depending on what kind of substance is absorbing that radiation. and it also depends on whether it's alpha, beta, or gamma, right? Each of those has different energy levels, will do different amounts of damage. So the most common one that's used in health would be REMs, right? Not the band or rapid eye movement or anything, but the radiation equivalent for man. All right. So this is the amount of radiation that's being absorbed by something, but it also happens to factor in the type of radiation and the energy of that radiation, as well as its potential for tissue damage. So what this means is that if I say that I was exposed to 1 rem of radiation, I know how much damage that is. It doesn't matter what type of tissue was, it was absorbed by. It kind of standardizes the amount of damage that's actually done. So it turns out that the average, person in the U.S. is exposed to about 0.27 rems of radiation per year. So not a whole lot. Now, again, I mentioned earlier that there is no really safe level per se, right? But that's the probability of anything happening from that low of a dose is very, very, highly improbable. So what happens? What are the effects of radiation? Well, typically, if you are exposed to between about 0 and 25 rems in a single dose, there are really no detectable effects. You probably would go about your day and not even notice that anything happened. If you're exposed to about 25 to 100, right? So this is 100, at least 100 times your annual dose all in one sitting. You might feel a little ill. You'd get a temporary decrease in your white blood cell count, right? So you might be more susceptible to illness and so forth because it's damaging your bone marrow and the white blood cells and so forth. If you're exposed to between 100 and 500 rems, which is a lot, remember that you're only exposed to about 0.27 annually. But if you're exposed to that much, you typically get radiation sickness, nausea, vomiting, fatigue, and so forth. If you were exposed to, like if I just opened up a briefcase and somehow exposed myself, or a group of people to 500 rems all in one sitting, that's known as the LD50, the lethal dose for 50% of the population. So 50% of that group of people would be dead within a month by getting exposed to 500 rems of radiation in one sitting. And if I up that to 600, then 100% of the people would be dead. So again, notice that this is a huge difference, right, between what we're naturally exposed to annually, right, every year, versus how much would actually kill off, a person, a guaranteed death via radiation. Now, besides the fact that radioisotopes can actually be used to treat cancer, there are other uses for these in medicine. For instance, radioactive xenon can be inhaled by a patient and can be used to image their lungs to see how well they're functioning, if there are portions of the lung that aren't functioning or inhaling air. You can use technetium for bone scans, gallbladder function, to look for GI bleeding. Iodine is used for thyroids, problems, hyperthyroidism, and so forth. Radioactive phosphorus can be used to treat leukemia and lymphomas. Iridium is actually used to treat breast cancer, which is one of the reasons that the treatment is so expensive, is because iridium's about as expensive as platinum. So it's basically like taking a platinum, injection, very, very expensive. And then radioactive thorium can actually be used to test whether the heart is actually functioning properly. So some pretty significant uses for these, in medicine. Now, the next thing that we talk about with radioactivity would be energy production, right? So this would be like a fission reactor, like we have here in Seabrook. So there's a nuclear reactor there, and it works by fission. It actually takes a heavy atom, like uranium, and it will actually bombard that with neutrons, break it apart, and turn it into other things, right? So in the case of uranium fission, you can see that we have an atom or a nucleus of uranium here. You hit it with a neutron, and by hitting it, you're actually going to break that up, right? And so it splits the atom. So that's what fission is splitting the atom. And in the process, you make two new elements, right? Because you just broke that atom into pieces. And the really cool thing about this is you actually get 3 more neutrons. So each of these neutrons goes shooting off, and now that can hit other atoms of uranium, and each of those can split, and those can each give off, 3 more neutrons, and so you can get what's called a chain reaction. And at some point, this is a self-sustaining reaction where you have enough going on that it can continue to progress. And so they'll actually have like control rods, or they can use heavy water or different things to actually absorb the excess neutrons if they want to slow the reaction, or if they want to speed it up, they can allow more of those neutrons to go and do their work of splitting other atoms. Now, in the process of splitting this, besides producing some new elements and some neutrons, it also produces huge amounts of heat, tons and tons and tons of energy. In fact, I think I read somewhere that 1 kilogram of uranium, when you fission that, it comes out to about the same energy equivalent as something like 144,000 tons of TNT or something crazy like that. So there's a lot of energy that is stored up within the uranium itself. So very nice. Now, it does have a downside, right? That you do have radioactive waste after this, and you have to figure out what to do with this. You have to figure out whether to store this somewhere. Sometimes they'll just store it on site, or they can take it out into Yucca Mountain or something and bury it in the desert. But that is a significant problem and an issue, and we do have to figure out a good way to deal with this. However, nuclear power really is the most efficient, cleanest source of energy we have. Far more efficient than any other source out there. And living near a nuclear power plant isn't really a concern, because so little radiation is actually being released into the environment, because it is so carefully monitored. The next thing is that coal plants actually put out, I think, about 4 times as much radioactive material as a nuclear power plant, because it just releases like radioactive sulfur and other stuff. In fact, a lot of the naturally radioactive crud that's in coal ends up in what's called the fly ash. And in some places like New York City, I've heard that they actually use the fly ash to grit the paths and or the roads in winter. And so you're just taking the stuff that's radioactive and just throwing it out there, and no one bats an eye. And yet the idea of having a nuclear power plant where you're monitoring what's, if anything's being released, you're releasing far less. A lot of people freak out about that. You should also be aware that it is physically impossible to, have a nuclear power plant, go off like a nuclear bomb. It's very, very different. In fact, different isotopes of uranium even. So it doesn't work that way. Any explosion that occurs typically occurs because there's a buildup of heat, right? Like at Fukushima. So because the coolant system went offline with the tsunami and so forth, there's this buildup of heat, which can end up generating a lot of steam, which can then explode, right? And again, not a nuclear blast, something very different. Now, the other option, though, would be, instead of fission, we could actually work with fusion. So fusion is where we actually take light nuclei, like in the case of the sun takes deuterium and tritium, 2 forms of hydrogen, actually fuses these together to form helium, and then it gives off a neutron. So in this case, there would be no radioactive waste. You'd simply have a lot of helium that you could fill up party balloons and say, yay, we've got clean energy. And it produces like huge amounts of energy, more than fission does. However, you have to basically have a miniature sun inside the reactor. Extremely high temperatures and pressures. Right now, there's no feasible way to use this or to harvest it as energy, but hopefully someday we could, and that would solve all of our energy problems. In the meantime, we probably should just keep exploring different alternative energies, making things more efficient, and investing in cleaner coal, making sure that we have nice, safe nuclear power plants, new ones that actually follow all the current safety protocols and so forth. because we do have some energy, an energy crisis that we do have to deal with. So to end on a happy note, I'm going to go ahead and show you a quick trick. It's kind of like fusion, right? So what you see here is I have some money, right? $1, $2, $3, $4, $5, and yet do a quick little reaction here, and suddenly, I've got a 10, a 50, a 20, another 50, and a 5. So again, fusion is nice, right? You can get a whole lot of energy out of it for a very, very low cost if you could actually make it work. So if you do happen to somehow come up with a feasible fusion reactor, go ahead and let me know. I'll patent it. I'll give you a whole lot of extra credit. We'll all be happier. All right, awesome. So I hope you've had as much fun as I have in dealing with nuclear chemistry. Thank you.